Today we're going to continue our discussion on the Bohr model of the atom. If you remember, the last time we saw each other, Bohr improved upon, if you would say it that way, the Rutherford model of the atom. Of course, the nucleus, that positive dense center of the atom, is present, but the electrons actually orbited the nucleus a fixed distance from the nucleus, and we call these distances energy levels. The ones closest to the nucleus, or the one closest to the nucleus, he called the first energy level, and then we had the second energy level, third energy level, and so on. And Bohr determined this by understanding a little bit about the behavior of light. Hydrogen has only one electron. That's why Bohr chose hydrogen to work with. And if he could excite that electron to a higher energy level, let's say it goes to the third energy level, it requires energy. Now that electron doesn't stay there. It'll eventually fall back down. Now it can fall back down from the third to the second, or maybe from the third all the way back down to the first. In each case, it will give off a different amount of energy depending upon the energy level difference. So from the third to the second energy level, the energy given off will not be as great as from the third to the first. So I'm going to make the waves, the wavelength, different. So from the third to the second, we're going to have a bigger wavelength, right? That's less energy of light being given off. From the third to the first, of course, we'll have a smaller wavelength of light being given off. And, of course, different colors of light have different wavelengths, so Bohr could determine the energy by the color of the light that was given off. Now, I asked you to watch some demonstration videos on the emission spectrums of hydrogen, mercury vapor, and neon. And we're also going to throw helium in there, although we didn't see that particular demonstration. So we're going to view a picture, an image, of these emission spectrums. And as we do that, would you write down the colors of the lines that you observe for each of these? Because remember, different colors are different energies. So we could calculate the energy level difference based upon the color of the light. So let's go to that picture now. Here we go. And so for the hydrogen spectrum, it looks as though we see some red light being given off. By the way, that's a bigger wavelength. Isn't red light lower energy than violet light? We see this, I don't know what you want to call that, an aqua-colored light. Did you see that in the demonstration video? And then we see a blue band, and we see some violet light being given off. Much higher energy. So this must be the result of a big energy level drop. This must be the result of a small energy level drop. For mercury vapor, looks like we saw some yellows. Looks like we saw some greens. Here's a different color aqua than we saw for hydrogen. The wavelength is slightly different for this aqua than this aqua. We see some blue again. And we just see a couple of bands in the violet spectrum. Notice that hydrogen does not have the same spectrum as mercury. Then we saw neon, and neon was really cool. Didn't we see a whole bunch in the red and the orange and the yellow part of the spectrum? Very little over here, if anything at all. Helium, looks like we saw some red, saw some yellow, which was different, a little bit different than the yellow we saw in mercury. Looks like we saw some greens and blues. It's interesting to note that the element helium was not discovered on Earth. Helium was actually discovered on the sun. And when I say that, sometimes students have to scratch their head, well, how did we get to the sun and bring back some helium? Well, we didn't actually go to the sun, but can't we do a spectral analysis of the sunlight? And if we see a pattern, like we did for helium, that we'd never seen before on Earth, that means we had discovered a new element. And that was named after the Greek god for the sun, Helios, and it became the name of the element became helium. Isn't that interesting? Helium was discovered on the sun before it was discovered here on Earth. So, hopefully, you guys wrote down those colors that you saw for the spectral lines for hydrogen, helium, mercury, and neon. And the important part here is, were any of the spectra identical? No, they were not identical. Every element has its own unique spectrum. It's sort of a fingerprint of an element. Every element has a different spectra because they have different energy levels and different numbers of electrons that are moving in those energy levels. Where was helium first discovered? Of course, we just said that. It was discovered on the sun. And of course, how was it discovered? Through analyzing the sun's emission spectrum. Emission spectrum. And we found a pattern that we had never seen here on Earth before. And so we were able to identify a new element. Okay, before we continue, I want you to make sure you watch the next demonstration video called Flame Tests, and you're going to see something interesting when we do a flame test instead of an emission spectrum. So instead of passing electricity through gases, we're actually going to excite these atoms by heating them up, and we'll see different colors of flames being emitted for sodium, potassium, copper, strontium, and lithium. And of course, hopefully you can answer the question, what causes those different colors? All right. I think that's good enough for today, kiddos. See you soon. Bye-bye.